Hello everyone, thank you very much for attending my talk at MSGC 2021 Fall Conference. This is a joint work with the graduate student Mr. Manzoor and my colleague at the University of Michigan-Dearborn, Dr. Rawashdeh. The focus of this talk is on identifying the nonlinear dynamics of tethered subsatellite deployment maneuvers. Before proceeding further, let's take a look at this animation from the STS-46 shuttle mission. As you can see from this animation, there is a mothership and there is a subsatellite that are connected to each other via a wire, or what they call the electrodynamic tether, or EDT. A current is being conducted in a controlled fashion through the wire, and because of the flow of the current, an interaction with the magnetic field of the Earth would happen that would produce a propulsive force on the subsatellite system. And the physical principles of operation are exactly like electric motors. Now, the good thing about the electrodynamic tethers is that they provide a fuel or propellant-free propulsion method for satellite systems, and they can also overcome atmospheric drags. Because of this, tethered subsatellites have found applications in miniature satellite applications. For instance, in an initiative by the University of Michigan, CubeSatellite tethered system, which was called MIT-EE, was developed, and the idea was based on deploying a picosatellite body of approximately 8 cm by 8 cm by 2 cm from a 3U cubic sat. Of course, the first important aspect of being successful in deploying a subsatellite tethered system is launching the tethered satellite system and deployment of the tethered system into the orbit in a successful fashion. Now, this process of deployment is very challenging in general because there are many unknown perturbations and disturbances that might be acting on this deployment process. One of them is due to differential aerodynamic drag forces because of the difference in satellites' altitudes. Another type of disturbance might be a variable Lorentz force, which is generated by the EDT due to solar wind and geomagnetic storms, or it might be the case that either the subsatellite or the mothership might be subject to solar radiation pressures. Because of these, it is really important in being able to identify the underlying nonlinear dynamics of the subsatellite system and the subsatellite deployment maneuver. So, equations of motion of this subsatellite deployment maneuver are given using these nonlinear equations, which are coupled with each other and they are under-actuated, meaning that there is only one control input and 3 degrees of freedom, which are the angles theta and phi, which describe the geometric configuration of the subsatellite with respect to the mothership, and the controlled current through the EDT, which would control the length of this basically EDT. And not only we have got control forces, but we have also unknown disturbances that might be acting on the subsatellite system, and if not known or if not approximated, they can devastate the deployment mission. In order to be able to successfully control the deployment procedure, it is important to identify these nonlinear dynamics, because if we are successful in controlling these nonlinear dynamics, identifying these nonlinear dynamics, then we can use powerful model-based control techniques such as model predictive controllers that are extensively used in autonomous vehicle applications. Now, the tool that we used in this project on identifying the nonlinear dynamics of the subsatellite deployment maneuver was based on using Koopman operator theory. Basically, Koopman operator theory is a data-driven approach for approximating the unknown underlying nonlinear dynamics which might be subject to unknown disturbances. Specifically, if we have got a nonlinear dynamical system with the unknown flow F, and we have a bunch of measured data captured via the matrices of the data snapshot X and X prime, the idea of the linearized dynamics approximation using the Koopman operator theory is finding a matrix A that can approximately capture the flow of data under the nonlinear dynamical system whose dynamics are unknown. Now, the overall algorithm in the context of subsatellite deployment maneuver for identification of these nonlinear dynamics is given in this slide. As you can see, we have got snapshots of data captured through the matrices X and X prime at different time samples. Each column of these matrices include the data of the geometric degrees of freedom theta and phi, and the tether length, and also their rates of change. And through the Koopman operator based approach, we would find the matrix A, which basically approximates the linear flow of the system. And this matrix is obtained by solving a minimization problem over the Frobenius norm of the measured data. Now, once we obtain these linearized approximation to the nonlinear dynamics, which is captured by matrix A, then we can use a plethora of tools from the model-based techniques such as adaptive control or model predictive controllers in order to control the subsatellite deployment maneuver. Now, let's see some simulation results that we obtained for basically system identification, in this case using the Koopman operator. So as you can see from the figures, the first set of simulations were based on uncontrolled dynamics, meaning that there were no control forces acting on the EDT, and the only forces that were acting were sinusoidal disturbances. The nonlinear model is generating the blue lined data, and the linearized dynamics which is obtained from applying the Koopman operator theory is giving us the black lines. As you can see, there's a very good overlap between the linearized dynamics and the data which is generated by the nonlinear model. In the second set of simulations, we basically started controlling the current which was flowing through the tether. Specifically, we used a very simple proportional derivative controller to control the current passing through the EDT. And we increased the length of the tether from 0% to around 45%. As you can see, also the oscillations in the geometric angles theta and phi also died off as the deployment process was becoming more and more successful. Also, the whole mission was subject to unknown disturbances. Specifically in this case, there were sinusoidal disturbances. Again, the blue line represents the nonlinear model and its generated data. The black line represents the DMD linearized dynamics. Again, there is a very good overlap in between all these linearized dynamics and the underlying nonlinear model. As the next step to this research project, we aim to use our linearized dynamics, and by using it, design adaptive controllers and model predictive controllers in order to control the sophisticated motion of the subsatellite deployment maneuver. And it would be the subject of our future work. With this, we would like to I would like to thank my student Waqas Manzoor and my colleague Dr. Samir Rawashdeh, and I would like to acknowledge the Michigan Space Grant Consortium and the NASA grant that supported this research. Thank you very much for your attention, and have a wonderful day.